let's look at motion where the trajectory has a constant magnitude. Let R describe a path on which the magnitude of R is constant. Now, when the magnitude of R is constant, that means we have motion on a circle or motion on a sphere. In this case, R dot V will be 0. That means that the position vector R and the velocity vector V will be orthogonal at all times for which the functions are defined. So let's look at that situation. Let's say that R, the magnitude of R is constant. That means that the magnitude of R squared is a constant, and we'll just call that some constant C. But the magnitude of R squared is the same thing as R dot R. So now I want to take the derivative of both sides. I want the derivative of R dot R. Now we're assuming that the R is a function of t. And that's going to be the derivative of the constant C. Well, we know the derivative of a constant is just 0. The derivative of a dot product will be R prime times just R of t plus R of t times R prime using one of our product rules. Well, that's just 2 times R prime dotted with R equal to 0, which means that R prime dot R is equal to 0, which means that the velocity dotted with the position function is 0, which means that the velocity and the position are orthogonal. So that's true anytime we have motion on a circle or along a sphere. Okay, now let's look at a trajectory described by this. What I want to look at is I want to show that the object moves on a sphere. Now, if we're told that this is the trajectory of the object, we can just need to find that that actually satisfies the equation of a sphere. Well, remember the equation of a sphere. X squared plus y squared plus z squared has to equal to some constant, which ends up being the radius of that. So let me just use r. Well, now this trajectory is telling me that x of t is given by 3 cosine of t, y of t is 5 sine of t, and z of t is 4 cosine of t. So now let's see if that actually satisfies the equation of a sphere. So we'll have the x value, 3 cosine of t squared, plus the y value, plus the z value, and that should come out to be a constant if we're actually on a sphere. So now we have 9 cosine squared plus 25 sine squared plus 16 cosine squared. Now simplifying, we've got 25 cosine squared, adding the first two together. And when you factor a 25 out, you'll have cosine squared plus sine squared, which we know is 1, and this gives us 25. So these three functions do satisfy the equation x squared plus y squared plus z squared equal to 25. So the motion of that trajectory is on the outside of a sphere with radius 5. Now I want to find the velocity and the speed of the object. Well, we know velocity is just the derivative of the position function. which will be -3 sine of t, 5 cosine of t, and -4 sine of t. So that gives us our velocity function, our velocity vector valued function, and the speed is the magnitude of the velocity. Square root of 9 sine squared plus 25 cosine squared plus 16 sine squared. Which is the square root of 25 sine squared plus 25 cosine squared, which is 25, square root of 25, which is 5. So our speed is constant the entire time that we're on the surface of this sphere. Now, another thing, verifying that last theorem that we did, when you have a constant position, the magnitude of the position function is constant, which in this case it will be also, it's constantly 5, then we should have that the velocity and the position function are always orthogonal. So let's check that. So v dot r, so the dot product, here's r and here's v, will be -9 sine times cosine plus 25 sine times cosine plus minus 16 sine times cosine, which gives me just 0. So that does mean that the velocity and the position functions dot product is 0, so that means the velocity and the position are always orthogonal. And if you want to check to make sure the magnitude of the r was actually a constant, it'll be the square root of 9 cosine squared plus 25 sine squared plus 16 cosine squared, which also comes out to be 5. So let's look at two-dimensional motion in a gravitational field. Consider an object moving in a plane with a horizontal x-axis and vertical y-axis. The only thing acting on that is gravity. Now, given the initial condition, when t equal to 0, the velocity will be u naught v naught, and the initial position, r at t equals 0, is x naught y naught. We want to find a representation for the velocity and the position function. Now, if the only thing acting on the object is gravity, that means that the acceleration vector can be given by 0, -g. We will use this acceleration then to find the velocity. Since acceleration is the derivative of the velocity, that means that the velocity will be the antiderivative of the acceleration. So the integral of 0, -g will be just a constant in the x first component. Now, to have a derivative of 0, we had to have had just a constant. So we will have still just a 0 here. The derivative of 0 is 0, and then minus gt for the second component, but we'll have that plus constant vector, c1, c2. Now, we're given an initial condition. We know that this is v of t, but v of 0 is u naught v naught. So put 0 in. Remember, this is just v of t. Let t equal to 0, and we get v of 0 equal 0, 0 plus c1, c2. But v of 0 is u naught v naught, which means that is C1, C2. So C1, C2 is U naught, V naught. So our velocity function, which was 0 minus GT plus U naught, V naught, will be just U naught, comma, V minus GT. V naught minus GT. So that's our velocity function. And that's exactly what we have right here. So now, that's GT, not G of T.